What is going on, guys? My name is Amos and I'm back again with another video. So in today's video we want to talk about complex numbers. So first of all, what is a number system? So a number system is just a way of representing numbers. Alright, now you might be familiar with some number systems. For instance, the set of all positive on the set of all positive or numbers. So set 1, 2, 3, 4, and so on and so forth. And this is very useful for counting discrete quantities. Like for instance, if you have 10 books in a row, you can say, oh, I have 6 books, I have 4 books. All right, this is the set of positive or numbers. Okay, great. Now, sometimes zero is added to this set of numbers. All right, but that's rarely the case. But it's just something that you have to know, that sometimes zero is added into this set. If you want to get your set without zero, some people like to distinguish between n and n star. All right, so n star means excluding zero. All right, so this is one set of numbers. We also have another set of numbers which is known as the set of integers. All right, now this is the set of uh, 0, and then we have positive or numbers, and so on and so forth, and then we have negative or numbers. Now this is also another system. I think you already know. We also have you already know. I think we also have the set of rational numbers. Rational numbers. This is a set of numbers that can be expressed in the form p over q. So this is the set of numbers that can be expressed in the form p over q. In this case, numbers that can be expressed in this fractional form where q is not zero, because you know division by 0 is criminal. So we also have another set of numbers that is what you guys, I believe, use most of the times. So this is the set of real numbers. Now this is the set of numbers that contains numbers with decimal points, numbers with radix points, and so on and so forth. So we have 0, and then we have 1, and between 1 and 2 you can have something like 0.5, then you can keep on going here, and then you can have -1, -1.5, and you can keep on going here. All right, you also have things like the square root of 2 in this set, the square root of 3, numbers that are found in between. All right, so that is the set of real numbers. We also have the set of extended reals. Okay, now this is the set of real numbers, that is R bar. Now we have the set of real numbers, and then we append the two infinities. That is, we have positive and minus infinity. If we append the two infinities, we are going to get the extended reals. So that is appending positive and minus infinity. Now this set of numbers is known as the extended reals. All right, now today we want to introduce something new. We want to talk about the set of complex numbers. Now the set of complex numbers is a natural extension of the real number system. So it extends the real number system with the help of what we call the imaginary unit. Now the imaginary unit I verifies the equation I squared is equal to -1. Now it is here that I would like to talk about one difference. If in engineering, specifically electricity, using the letter J is common for the imaginary unit. This is because in electricity, I means electric current. So to avoid confusion, between the electric current in electricity and the complex unit, the letter J is used instead of I. Now I'll be using both of them in this video, so just you remember, so to make you remember the difference and why we use different the different notations. All right. Now that is great, but now the question still stands: why using complex numbers? Well, complex numbers are very simple to work with. So in electricity, we talk about RLC circuits. Now these RLC circuits, if you've done these RL circuits before, you know that we deal with a lot of differential equations. Now it becomes complicated to integrate, and it becomes complicated integration wise and differentiation wise. So it's easier to work with complex numbers because they are easier to differentiate, and they are easier to integrate, and they are easier to work with. All right. So now, having talked about that, let's talk about the general form of a complex number. What is the general form of a complex number? The general form of a complex number. So the complex number, we use Z to denote a complex number most of the times. Now you can use any letter you want, because you have it in mind that you're going to define a complex number. I'm going to use Z in this video. So Z is equal to A plus now BI. Now this is a complex number where A is known as the real part of the complex number. The real part of the complex number. A is known as the real part of the complex number. So we have R. This means real part. All right. The real part of Z. The real part of the number Z is A. Then the imaginary part of the number Z is B. So, however, A and B are real numbers. A and B are real numbers. Great. So A and B are real numbers. So this is the form of a complex number. A complex number is a number that is written in this form, A plus BI, where A is the real part of Z and B is the imaginary part of Z. All right. Now, having talked about that, we can also solve, some questions, knowing that the complex unit, the complex unit that is I or J, J squared has to verify this equation -1. So what does this evaluate to? So what does J to the power 3 evaluate to? So we know that J to the power 3 is J to the power of 2 multiplied by J. Now J to the power of 2 is -1 multiplied by J. So this is minus J. Let's try another one. J to the power of 8 is J to the power of J to the power of 8 is J. Let me just wrap that. All right. J to the power of 8 is J to the power of 2 multiplied by 4. Right. Now, what is J to the power of 2? J to the power of 2 is -1 to the power of 4. Now, 4 is an even number. -1 to the power of 4 gives us positive 1. All right. Now, let's try another one. Something that is a little bit more complicated. Let's try J to the power. It's also simple, I think. Something like J to the power of 23. What is J to the power of 23? J to the power of 23 is J to the power of 1 multiplied by J to the power of 22. Now, J to the power of 1 multiplied by, now this can be written as J to the power of 2 multiplied by 11. Now, J to the power of 2 evaluates to -1. -1 raised to the power 11, which is an odd number. So it has to be -1. -1 multiplied by J minus J is your result. So these are some of the basic problems you can solve. And now you are a master at complex numbers. All right. Now, let's talk about the equality of two complex numbers. When are two complex numbers equal? Now, on the complex plane, two complex numbers are equal if they represent the same point on the complex plane. Now, that means that if you have two complex numbers, Z1 is equal to A1 plus B1I, and Z2 is equal to A2 plus B2I. Now, for them to represent the same point on the complex plane, it has to be that the real part, all right, the real part of A, the real part of Z1 has to be equal to the real part of has to be equal to the real part of z, z2. And the imaginary part, great. The imaginary part of z1 has to be equal to the imaginary part of z2. Now, when this happens, these two complex numbers are going to be equal. The two complex numbers are going to be equal. Now, this reads as this z1 is equal to z2 if and only if the real part of z1 is equal to the real part of z2. The imaginary part of z1 is equal to the imaginary part of z2. Now, there's another way of thinking about complex numbers notation-wise. Instead of always writing them in the form a plus bi plus bi, you can also think about complex numbers as a set of pairs. So, for example, the complex number z is equal to x plus bi can be thought of as z, which is a point on the complex plane, that is x, y. You can also think of complex numbers like this. So now this is very useful because it cuts down a lot of writing things and so on and so forth. So you can think of a complex number as a pair of as an ordered pair, that is x and y in our case. Now, how do you add two complex numbers? So it's very simple to add two complex numbers. Well, you just have to add their real parts alone. Then you come and add their complex parts. Let's take an example. So if z1 is the complex number a1 plus b1i, and then z2 is the complex number a2 plus b2i. Now, if you want to find z1 plus z2, simple. You just have to add the real parts. So that is a1 plus a2, and you add the imaginary parts. So that is b1i plus b2i. So this is going to be a1 plus a2. You can factorize by I here. So you can have b1 plus b2i. Now this looks a little bit messy and not clear to see that this is maybe a complex number. So you can say let a1 plus a2 be equal to, let a1 plus a2 be equal to c. And then you can also say let b1 plus b2 be equal to d. And we can also say we let z1 plus z2 be equal to z. Now this simplifies to z is equal to c plus di. Great. So now you can easily see that this is a complex number. All right. Now this is for you. This is for you to see what is going on here, because you might not easily see what is going on here. All right. So that is how we add two complex numbers. So let's take an example. Now I'm going to take a very simple example. Let's take the example z1 is equal to 1 plus 2j, and z2 is equal to 2 plus 3j. Great. Now I'm now using j instead of I. Okay, so let's say z1 plus z2 will be equal to, so the real parts, that is 1 plus 2 plus 2j plus 3j. So that is z1 plus z2 is going to be equal to 1 plus 2 is 3. Now here you can factorize by j and add 2 to 3, so you'll get 5. Or for now, let's write it like this. So it's going to be 5j. So this is your result of adding z1 to z2. Great. Now let's talk about, if you want to subtract the complex numbers, if you want to subtract these two complex numbers, it's also easy to subtract the two complex numbers. You just have to subtract the real parts and subtract the imaginary parts. For example, if you want to find z1 minus z2, you can say, oh, z1 is what? z1 is 1 plus 2j. What is z2? z2 is minus, z2 is 2 plus 3j. Now you expand here, 1 plus. Now I'm going to bring the 2 here because I have to add to subtract the imaginary parts. And then we have 2j minus 3j, which looks good. Now 1 minus 2 is minus 1. Now what is 2 minus 3j? 2 minus 3j is minus 1. So that is minus j. Great. So that is how you subtract two complex numbers. And that is how you add them. So let me just take care of this part so that we can move to something new. All right. Great. So now let's talk about the algebraic properties of complex numbers. It is very important to know these things. So let's talk about things like associativity. Now, if I give you 3 numbers, all right. Now we'll talk about associativity with respect to addition and with respect to multiplication or multiplication. So let's talk about associativity with respect to addition. So let's say you have 3 complex numbers. So Z1, Z2, and Z3. Wait. Great. So Z1, Z2, Z3 are your 3 complex numbers. All right. Now, what associativity by addition tells us is that the order in which you add these 3 complex numbers is not important. For example, you can say Z1 plus Z2 plus Z3. Now, you can first of all start by adding Z2 to Z3 and adding the result of that to Z1. Or you can say this is Z1 plus Z2 and you add the result to Z3. So that is what associativity by addition tells us. Now, what is associativity with respect to multiplication or multiplication? So associativity, still the same principle. You have multiplication here. Great. Now, if you are given 3 complex numbers, so Z1, let's use the same Z2 and Z3. Now, the order in which you multiply them is not also important. You still get the same answer. So Z2 multiplied by Z3 is going to give you Z1 multiplied by Z2, Z1 multiplied by Z2. So Z1 multiplied by Z2 multiplied by Z3. The order in which you multiply them, not important. You still get the same result. Now, that is associativity with respect to multiplication. So let's also talk about commutativity. So this has to deal with things changing positions. All right. So let's talk about commutativity. Commutativity. So if you are given 2 complex numbers, so Z1 plus Z2 is equal to Z2 plus Z1. Now you can change the positions of Z1 and Z2. You still get the same result. Now we also have commutativity with respect to multiplication. So that is Z1 Z2 is the same as Z2 multiplied by Z1. Now here, let me just tell you something about complex numbers that is really, really important. Now it comes from this commutativity with respect to multiplication. Notice that writing A plus BI is the same as writing A plus IB. All right. Now let's see what happens. Let's take Z1. Let's take Z1 as I, as the complex unit. And let's say Z2 is equal to the complex number Y. Now, if I substitute in this equation, I'm going to have IY is equal to YI. Boom. You have that IY is equal to YI. So you can write it. You can write your complex number like this and like this. It's still the same thing. And complex numbers where the real part is 0. If you have the real part, if this part is equal to 0, then the complex number is known as a pure imaginary number. Great. So that is about commutativity. And another thing is the identity element. So what is an identity element? An identity element is an element which, if added to something, you're going to get back that same thing. For example, in in the context of complex numbers, we want to look for an element in the set of complex numbers such that if that element is added to another complex number, we get back that same complex number. That is, let's say, now here we have to distinguish between the identity element with respect to addition and with respect to multiplication. With respect to addition, we know that this is evident. Z1 plus 0 is going to give us Z1. So therefore, this means that 0 is identity by addition. Identity by addition. And if you see with respect to multiplication, we know that Z1 multiplied by 1. Now, what is 1? 1 is a complex number where the real part is 1 and the imaginary part is 0. So this is still going to give us Z1. This means that 1 is identity. 1 is identity by multiplication. All right. 1 is identity by multiplication. We can also talk about the additive inverse. So what is an additive inverse? So if you have two complex numbers, let's say with respect to addition, you have Z1. How do you get back the identity element? We know that if Z1 is the complex number X, Y, so I'm thinking about complex numbers as an ordered pair on the complex plane. So that is Z1. So the additive inverse of Z1 is minus Z1, which is minus X minus Y, because we know that if you add these two things, you get 0, which is the identity element. So this means that Z1 is the additive inverse of minus Z1, and minus Z1 is the additive inverse of Z1. So that is what is going on here. So how about the additive, the multiplicative inverse? So it is not obvious for the multiplicative inverse. So, but we know beforehand that if a number is said to be a multiplicative inverse of another, we must have that Z, which is our complex number, multiplied by that same multiplicative inverse. Then we must get the identity element with respect to multiplication. So that is 1. All right. So how do we get this behavior? So we can generalize. We can come up with expressions of what Z1 is going to be. All right. So let's try that. So let's say Z is the complex number defined by the ordered pair XY. Now here we have multiplication, and Z minus, which is the multiplicative inverse of Z, is defined by the ordered pair UV. And now this has to satisfy this 1, 0. We know that 1 is the complex number where 1 is the real part and 0 is the imaginary part. So we have this equation. So what is going to be our result? So let's take care of this. So I'm just going to transform a little bit notation wise. So let me say that x is x and yj multiplied by u plus vj, and now this is just 1 because the imaginary part is 0. Now, how do you multiply two complex numbers? Well, multiplying two complex numbers is very simple. You just have to assume that you're multiplying real numbers, the same way you multiply these things. And then you have to use the relation j squared is equal to minus 1. So let's try that. So x times u is xu, x times vj is that is xvj, yj times u, that is plus yuj. Now y times v, now j multiplied by j is minus 1. Remember, use the relation j squared is equal to minus 1. So j times j is minus 1. Y times v is yv, but minus yv. Now this has to be equal to 1. All right. So let's regroup. So we have xu minus yv, great, plus that is xv plus yu and j. So that has to be equal to 1. Great. So now let me transform back to our notation. Let me just take care of this part. So here we have xu minus yv. Great. So we have xu minus yv. If I think about this complex number as an ordered pair, comma, that is xv plus yu. Now this has to be equal to 1, 0. Now this means that xu minus yv is equal to 1, and that xv plus yu is equal to 0. Now we are going to solve a system of equations, that is a system of two equations, and in this case the unknowns are u and v because we want to find the expression of z minus. Therefore our unknowns are u and v. So we have to solve this systems of equations. So we have this, then we have xv. We have xv plus yv equal to 0. So if I want to eliminate the first part, this is xu, sorry, it's not xv. So this is xu, this is xv. So if I want to get rid of let me just write things properly here. So we have xu, great, minus yv, great. Now this is equal to 1. And here we have xv, great, plus yu. This has to be equal to 0. Okay. Now here the unknowns are u and v. So the way we solve systems of equations, you can think of x and x here as numbers. You can think of them as numbers. All right. So how are we going to solve these systems of equations? So we have methods which we can use to solve these systems of equations. We have elimination, we have substitution, we have all those good things that we can use to work around this problem. So how are we going to apply? So you can choose a method. So let's say we want to use the elimination method to solve this problem. How do we use elimination to solve this problem? Notice that we have to eliminate one part. Here we have to eliminate one part. Now, how are we going to do that? Now, notice the way I've written this. We have xu, we have xv. I've just said that u and v are unknowns, so we just have to change position. So let's just have u here and vv. Great. So now let me just wrap the second part. Let me just write it the way I have said it. So here we have yu plus xv is equal to 0. So by elimination, notice that I have to multiply the top part by y. I have to say, all right, let me just multiply. This is going to be y, and then this is x. So we're going to have xy u minus y squared v is equal to y. And then here we'll have xy u, and here we have x squared v is equal to 0. Now you just have to subtract these two equations. So by subtraction we get minus y squared minus x squared v and y. Now to find v, let me just take care of the top part. All right. So to find v, you divide by minus y squared minus x squared. So now why is it possible to divide? Because we know that minus y squared minus x squared is not 0. This is because z is not 0 by definition. If you look at our stat, so here we have that v is going to be equal to y divided by minus x squared minus y squared. Now this is the same as minus y over x squared plus y squared if you multiply by minus 1 at the top and at the bottom. So that is your v. Now let's also find our u. So I'm just going to use the same systems. So let me just wrap this part. Now the goal is to find u. So we have to eliminate the second part. So I'm going to multiply x here and y here. So this will give me x squared u minus xyv is equal to x. And then here we should have y squared u plus xyv is equal to 0. Now, if I add these two equations, this part is going to disappear. So we're going to have xy plus y squared, great, u. Now, this is 0, and this is equal to x. So u has to be equal to x over. Now, this will be a little unclear. Let me just take care of the top part. And that will be u is equal to x over x squared plus y squared. Great. Now this means that z minus, if you think of it as an ordered pair, it is going to be uv, that is x squared plus y squared, comma, and minus y, x squared plus y squared. Great. Now this is going to be your multiplicative inverse. Now this is the general expression, okay, works for any complex number. Now let's also talk about something very, very important, the component of what is known as the complex conjugate. So what is the complex conjugate? What is the conjugate of a complex number? So if you have a complex number z equal to, that is x plus jy, the number z bar, which is equal to x minus jy, is what is known as the conjugate of the complex number. Sorry, that is what is known as the conjugate of the complex number. So you just have to change the sign. So there you go. You have your conjugate. So you change the sign of the imaginary part. You get your complex conjugate. Great. Now that is good. And now, how does this help us? So it is because we have to talk about something known as the division of complex numbers. How do you divide two complex numbers? So to divide two complex numbers, you have to use the idea of the complex conjugate. Note that if you multiply a complex number by its conjugate, the result is always a real number. If you multiply a complex number by its conjugate. Now let's look at an example of how to divide complex numbers. So if you want to divide 2 minus j5 over 3 plus j4. Now you have to multiply the complex conjugate of the denominator at the top and at the bottom. So this is going to be equal to 2 minus j5 multiplied by, what is the conjugate of this? It is going to be 3 minus j4. Great. Now what is the conjugate of this guy? That is j4. And then multiplied by 3 j4. Now let's evaluate this. Now let's start with the bottom part. We know that we are multiplying a complex number by its conjugate. Now we should get a real number. Now how do you multiply complex numbers? Let me just do it here. So if you want to prove that the result is always a real number, you can multiply. So how do we multiply? We first of all imagine that they are real numbers and use their relation. J squared is equal to minus 1. 3 multiplied by 3, that is 9. Now j4 multiplied by 3, that is plus j12. Now again, we are done with that is 3 multiplied by sorry, we have a little problem here. 3 multiplied by 3, 9. 3 multiplied by that is minus j12. Now j4 multiplied by 3, that is plus j12. Now you can see that this part is going to go to 0, and j4 multiplied by minus j4. Great. Now this has to be minus j squared. 4 times 4 is 16. Now what is this? This evaluates to 0. j squared is minus 1. Minus 1 multiplied by this minus sign here, we're going to have positive. So we're going to have 9 plus 16. So this is equal to 25, which is 9 plus 16. Great. So we've taken care of this part. So we are going to have 25 at the bottom. Now let's evaluate the top part. Let's evaluate the top part. So we have 2 minus j5 multiplied by 3 minus j4. Now what is 2 multiplied by 3? 2 multiplied by 3 is 6. Now what is 2 multiplied by minus j4? That is minus j8. Now what is minus j5 multiplied by this guy? That is going to be minus j15. That is going to be minus j15. Now this is plus j. What is 5 multiplied by 4? 5 multiplied by 4 is 20. Great. Now we're supposed to have j squared here because we have j multiplied by, oh wait, this is minus j minus j. Minus j minus j, that is plus j, but j squared. And we must have, great. Now 5 multiplied by 4 is 20. Okay, so we know that j squared is minus 1. So this has to be minus 20. Now this has to be minus 20. So 6 minus 20. What is 6 minus 20? That is minus 14. Now, what are we going to get from 8 minus 15? Okay, so we can factorize by minus j. Great. And we can say 8 plus 15. Now if you multiply minus j multiply, if you do minus j multiplied by 8, you get minus j8, and you still get back this that is here. All right, so now what does this evaluate to? Let me just okay, I can write it here. So that is minus 4. Now minus j. Now 15 plus 5 is 20. 20 plus 3, that is 23. So you have minus j 23. Great. So now this is what we have. So this is minus 14 minus j 23. And now you can divide your 25 on the left part and on the right part. That is so that we have a complex number that is expressed in its general form. So this is like minus 14 over 25 minus j 23 over 25. If you divide, you should get minus 0.56 minus j 0.92. So that is how you divide two complex numbers. You multiply the complex conjugate of the denominator, that is at the top and at the bottom. All right, guys. Now let's talk about how to represent other ways of representing complex numbers. So far, we've just been dealing with the Cartesian representation of the complex number. Let's talk about another representation of the complex number. Let us talk about the polar representation. The polar representation of a complex number. What is the polar representation of a complex number? Well, it's very, very simple. We'll start from trigonometry. If you have a right-angled triangle, let me just help myself with what do I need? I think I need this guy. No, not this guy. I need this guy. Great. Now let me just rotate it, bring it here. You have to bear with me here. So I just want to be able to make a line. Let me just make a line. Great. So from trigonometry, we know that if you have this guy, okay, let me just move it there. We know that if you have this guy, all right, some more rotation. Great. Great. All right. So that looks good. So let me now get rid of this guy. Now, we know from trigonometry that if you have your angle theta, and this is your x, this is your y, and this is r, all right? We know that x is equal to r cosine of what? X is equal to r cosine of theta. Y is equal to r sine of theta. Y is equal to r sine of theta. Now, this is already known. And then we know that theta is equal to arctan of y over x. All right. Now, let's expand this to the knowledge of complex numbers. We know that the general form of a complex number is z is equal to x plus jy. All right. Now, what is x? X is r cosine of theta plus j. Y is r sine of theta. Now, we can factorize here by r, and we shall have cos theta plus j sine of theta. Now, this is what is known as the polar form of the complex number. This is what is known as the polar form of the complex number. And we also know from trigonometry that r is equal to the square root of x squared plus y squared. This is also known from trigonometry. Now, let's now talk about absolute values. Let's take the absolute value of what we have here. So the absolute value of z is the absolute value of r multiplied by cosine of theta plus j sine of theta. Now, the absolute value of a product is the absolute value of the individual parts of the product. So we should have cosine of theta, j sine of theta. Now, we know that this is, I'll talk about this later. Now, what is the absolute value of this? It is the square root of cosine squared theta plus sine squared theta. The absolute value of r. Now, we all know that this evaluates to 1. What is inside evaluates to 1? The square root of 1 is 1. Now, here, we know that r is positive. If you look at this formula here, r is positive. And the absolute value of r is equal to r when r is positive. Now, this is equal to r. Now, what does this mean? This means that r is the modulus of the complex number. Great. R is the modulus of the complex number. R is the modulus of R is the modulus of the complex number. Great. So now this is what we have as information. So that is your polar form. Now let's take an example. All right. So let's have let's give ourselves an example. So we have 2 plus j3. Now we know that we have to find r because z is given, has to be like this in the polar form, where we have the angle and we have r, which is the magnitude or the modulus, or vectorially it's the magnitude. Yes. So r is equal to the square root of 2 squared plus 3 squared. So r has to be equal to, now 2 squared is 4, 3 squared is 9, so this has to be 13. So that is the square root of 13. Now, how do you find theta? Well, we know that 2 and 3 are positive. Therefore, in the complex plane, this has to be in the first quadrant. So we must talk about the angle arctan of theta is going to be equal to arctan or tan inverse, if you wish. Others also like to distinguish between using uppercase A and lowercase a, but we don't want to worry about that. So let's just say that that is y over x. And theta is equal to arctan of 3 over 2. Great. Now this is equal to, after calculation, you should find 56.31 degrees. Great. So now this means that our z is going to be equal to the square root of 13. And now this is not a less than sign. And this is theta. Theta, or what is our theta? Great. Our theta is 56.31 degrees. So this is your complex number z in the polar form. Of course, in the third part, where we're going to talk about applications and more examples, we'll see more examples of this. What if it is found in the third quadrant? Or what value of theta must we take? What if it is found in the fourth quadrant? That is the objective of the third part, I think. Yes, where we are going to be doing more examples on what we are talking about, and the applications of complex numbers. Now let's talk about another representation of complex numbers, which is very, very important. That is the exponential form of a complex number. Now here we just have to admit a certain result. E to the power I theta is equal to cosine of theta plus I. Let me just use j once more. J sine of theta. We are just going to admit it in this video. We are going to show that this is actually true in the next video. All right. Now we have that e to the power I theta. Well, now since I've used j here, I need to use j here. Great. J e to the power j theta is equal to cosine of theta plus j sine of theta. Now from the polar form, we had that z is equal to r cosine of theta plus j sine of theta. Now what does this mean? This means that z is equal to r e to the power j theta. Now this is what is known as the exponential form of a complex number. This is what is known as the exponential form of the complex number. Great. So this is what it simplifies to in the complex form. So same calculation for in the polar form. You find r, the theta that we find from the polar form is what we put here. Now some people like to represent theta here in radians. And you must know that you must know how to convert from degrees to radians, and so on and so forth. So that is why it is important to have that information. All right, guys. Now, why talk about the polar form, for example? So it is because it is easier to work with complex numbers in the polar and the exponential form than the Cartesian form for some problems. It is easier to work with them like that. Now, let's talk about the polar form again. So you have your exponential form and your polar form. Let me just show you how easy it is to add to multiply and divide complex numbers. If you have z1 defined as r1 and theta 1, and you have z2 defined as r2 and theta 2, how do you multiply these guys? So it's just z1 multiplied by z2 is equal to, you multiply the r1 and r2, and you just add the angles, theta 1 plus theta 2. Simple. If you want to divide z1 and z2, so z1 divided by z2, or you just have to divide these guys and you subtract theta 1 minus theta 2. You subtract the angles. Easy. So this is why the polar form is important in this case. We'll also talk more about the exponential form in the next video. Otherwise, I'll see you guys next time. Thank you.